Hey students, in this video we're going to be talking about heat transfer and the heating or cooling curve, specifically of water. So as you see here, you see the heating curve for water, where you go from negative temperatures up to 0, and then from 0 up to 100, and then it boils, and then you go to above 100 degrees. So each of these are their own separate parts here, and as it changes direction, different things are happening at these changes of direction. So at the beginning, here, where the temperature is below 0, you have ice. This is just ice, okay? Here you have a very specific heat capacity for ice. You have 2.09, where is it? 2.09 joules per gram per degree Celsius. Okay, so that is a number that you are going to be given, so don't worry. That's the first number over there on the chart. So anything below 0 right there is going to have that specific heat. And if you're doing any sort of heat absorption, or calculating how much heat is being absorbed as it's heating up from a negative temperature up to 0, you're going to use that specific heat, and then you're going to use Q equals mc delta T. Now, let's say you're going from 0, where it's frozen ice, and you're going to melt all that ice. So that's where number 2 is, the plateau here. At 2, you have the heat of fusion here. So you have a formula where you have the mass times the heat of fusion, and this is going to give you the amount of energy needed to melt the ice. So you multiply again the mass of the ice that's being melted, and you multiply it by then the heat of fusion for ice, which is 334 joules per gram. Okay, so that's the second one. The third one is, now that you've melted the ice, if you're going from 0 up to 100, anywhere in between there, you have liquid water. So this is liquid. And you're going to be using Q equals mc delta T. Now the one main difference in this is that the specific heat for liquid water is different than for ice, and this is going to be 4.18, as it says here. Now, once we hit 100, we're now creating steam, and we're vaporizing that liquid water. And so we're at the heat of vaporization. So in order to figure out how much energy is required to make that steam, you have to multiply the mass of the amount of water you have, multiply by the heat of vaporization, which is here, and it's given to you, and that's 2,230 joules per gram. Okay? Again, these are numbers given to you. And last but not least, if you have steam and you're increasing the temperature of it from, say, 100 up to 120 or something, then you're going to have steam at that point, and you're going to use, again, Q is equal to mc delta T, and again, this has a different specific heat capacity for steam. It's 2.03 joules per gram per degree Celsius. Okay? So I know this looks a little bit complicated, but I hope you see that we have these three parts where it's increasing in temperature have all the same equation, Q is equal to mc delta T. And the only thing that really changes is the specific heat capacity and which temperatures we're, rising or falling to. And the other two are the heat of fusion here and the heat of vaporization here. And those just have different equations to use. All right, so we're going to use this, and we're going to go through some practice problems right now. So number 1, calculate the heat needed to raise 27 grams of water from 10 degrees up to 90 degrees. So here we have 10 degrees, so that's roughly here, up to 90 degrees. So it's all within this third part here, where you have liquid water. You're just going to use Q is equal to mc delta T. So let's try that. So m times c times delta T. This is equal to the mass, which is 27 grams, times C, which is 4.18 for liquid water, times the change of temperature. Now, the change of temperature is final temperature minus initial. In this case, the final temperature is 90, and we started at 10. So 90 minus 10. You multiply these together, and you're going to get 27 times 4 point, oops, sorry, 27 times 4.18 times, what is it, 80? 9,028.8 joules. Okay, so the units are joules for heat. Okay, number 2, how many kilojoules are required to heat 45 grams of water from 25 and then boil it all the way? So if we look here at the temperatures that we're given, we're going to start at 25, and we're going to go all the way through to boiling it, so all the way through here. So we're going to have two different parts, this liquid phase and then also this vaporization phase. So we're going to add two different equations. We're going to have the Q is going to be equal to mass times specific heat times delta T, and the heat of vaporization formula. Okay, so this is equal to the mass, which is 45, times C, which is the specific heat of water at this point, liquid water, times the change of temperature. Now the change of temperature for this part is going from 25 up to 100. So it would be 100 minus 25. And then we're going to add that to the mass, which is again 45, times, now the heat of vaporization is 2,230. And we're going to add that together. So 1,254, and then 45 times, oh shoot, I totally lost track. So 1,000, so that would be a total of 101,704. Now this is in joules. So to convert this into kilojoules, what it's asking, move the decimal place over 1, 2, 3 spots. So the answer in kilojoules would be 101.7 kilojoules. Okay. Next, calculate the amount of energy used when 33.3 grams of ice at 0 degrees Celsius is converted to steam at 150 degrees Celsius. So again, we go back to where we start. So if you look back here, right, it's important to take a look and figure out where we start. We started with ice, so we have to melt that ice first. And then we have to heat it up to 100 degrees. That's the second part. A third part is boiling it or vaporizing it. And a fourth part is going from 100 up to 150 degrees. So there's 1, 2, 3, 4 parts in this particular question. So we're going to take a look and add these. So it's going to be Q is equal to, first, the heat of fusion, that flat part, plus m times c times delta T, which is going up from 0 to 100, plus the heat of vaporization formula to vaporize the liquid water. And lastly, we're going to do another mc delta T to go from 100 up to 150. And then we plug it in. So 33.3 times 334 plus 33.3 times 4.18, which is the specific heat of liquid water, times 100 minus 0 plus 33.3 times 2,230. And then finally, we're going up from 100. Now that's steam, you go up to 150. So again, 33.3 times, in this case, 2, I don't know why this is messing up, 0.03. And then this is times 150 minus 100. Okay, so I'm not going to take the time to just plug that all in, but if you add up or multiply and then add up all of that, you should get your answer. It's going to be a big number, so I'd suggest you convert it to kilojoules. How many joules of heat are needed to change 50 grams of ice at negative 15 degrees Celsius up to 120 degrees Celsius, making it steam? And so again, this is a very similar problem. Instead of us starting at ice, we're going to start below 0 to negative 15. And this will be essentially the same thing, but all 5 in this case. So we're going to go from the mass, which is 50, and then 2.09, which is specific heat of ice. We're going to start at negative 15. All right, we're going to end at 0. So negative 15 minus negative. And then we add the mass times heat of fusion. So the mass again is 50 times 334. And then we're going to, now we figured out how much it takes to melt it. Now we're going to go from 0 up to 100. MC delta T. So 50 times 4.18 this time. And then that's 100 minus 0. And then we're going to go mass times heat of vaporization. So that's 50 times 2,230. And then last but not least, going up from 100 to 120, MC delta T. This is going to be adding 50. I'm not sure why this is, I'm going to put this down here. Not sure why it's messing up over here, but this is 50 times specific heat of steam, which is 2.03 times, and so it's going up to 120 from 100. Okay, and then you add all that up and you get your answer. Last but not least, we have this question. So you're cooling down. So I want to show you an example of this one. Okay, so calculate the number of joules if you're going to cool down. Well, in this case, you're going to start off at 110 and go down. So you're going to do MC delta T, but from 110. So 32 grams times steam's specific heat. And then the change of temperature is 110 to 100. So final is 100 minus 110, the initial. This is going to give you a negative number, right? And then you're going to do the next one, which is how much energy it takes to make sure that it is negative. So So we're going to subtract that. That's going to be m times heat of vaporization. So it would be 32 times heat of vaporization, which is 2,230 minus, again, now you're going to do mc delta T to do down from 100 down to 0. So again, 0 is my final, 100 is my initial. This would be, sorry, plus. And then you have minus again for your amount of energy it takes to freeze, so m times heat of fusion. And this will be minus 32. Oh my goodness. Folks, I don't know why this is really messing up, but we're going to try to stick with it. This will be 334. And then finally, we're going to go down from this mc delta T. Going from 0 down to negative 40. Okay, so adding all that up, you should get a negative joules. That indicates that there's heat released. Okay, there's an exothermic reaction. In the next video, we'll do one where you mix two liquids and you figure out the final temperature, and then we'll do a calorimetry problem.